What up, mathletes? All right, we're going to get into this. Today's lesson is 9.2.2, and the essential question is, how can I use inequalities? How can I use inequalities? And we're going to say, hey, I will consistently solve inequalities today. That's kind of my goal for you today. So I'm going to give you this problem. Check this out. X plus 2 is less than or equal to 3. Now, let me remind you, how do I solve this problem? Well, if I put an equal sign there, everyone would be like, oh, yeah, I just subtract 2 from both sides. Okay, then do it. Let's subtract 2 from both sides. Boom. Minus 2. And what do we get? Kind of wrote this a little bit too high, but you see it. I get x is less than or equal to 1. Boom. So what are we going to do? We're going to go to 1. Less than or equal to is what kind of a dot? Let me remind you. Closed dot is less than or equal to or greater than or equal to. And an open dot is less than or greater than. So at 1, we're going to do a closed dot because it's less than or equal to. And I'm just going to go up and draw, since it's less than, I'm going to draw an arrow left because those are all the numbers less than. Awesome. Good work. Let's take a look at this next one. So 2 times x plus 3, or x minus 3, excuse me, x minus 3 is greater than 4. A couple of ways I can solve this. I'm going to solve it for you both ways. Generally speaking, I think most of you would distribute this and say, all right, 2x minus 6 is greater than 4, right? Add 6 to both sides. We get 2x is greater than 10. And then I'm going to divide both sides by 2. Boy, my pen is having problems. Let me get a new pen. See if this works. Come on, pen. It's because I'm writing on this rubber mat. And pens don't always like, you know what? How about we just switch to pencil? Probably should be doing that anyway. Okay, so I'm going to divide both sides by 2, and boom, what do I get? I get that x is greater than 5. See how we just solved it like we would any equation? And greater than is an open dot, so I'm going to go to 5, put an open dot, and an up arrow to the right because it's greater than. Boosh. Look at that. It's not perfect, but it works. I know I didn't give enough room for these, but all right, we'll live through it. Next one. This one's going to be kind of weird. I want to talk about this one. So this one is x squared is greater than or equal to 4. I want you to think about this. First of all, can you think of a number squared? Let's look at the problem x squared equals 4. Well, what number squared equals 4? Many of you are saying 2. If you didn't know what you can do, how do we undo a square? Square root, right? What square root of x squared is x. And square root of 4 is plus or minus 2. So here's what I know. I know that 2 squared is greater than or equal to 4 because 2 squared is 4. 4 is equal to 4, right? So I'm going to have an upper boundary, closed dot, at 2. But here's what else I know. Isn't negative 2 squared also 4? So negative 2 squared would be greater than or equal to 4. So boom, I'm going to have a closed dot at 2. Here's where I want you to think about it. I want you to think about this. We're going to blow our minds a little bit, but it's going to be good. Are you ready? Because this one's a little different. We're going to think about it first, and I'll show you how to solve it, okay? So what if I look at the problem 1? Let's try 1. What is 1 squared? It equals 1. Is 1 squared greater than or equal to, is 1 greater than or equal to 4? Nope. So that point doesn't work. What about negative 1? Negative 1 squared equals positive 1, which, is that greater than or equal to 4? Nope. So see, these values inside of here doesn't work, but let's try something else. What's 3 squared? 3 squared is equal to 9. Is that greater than or equal to 4? Check. So we know that if I go this direction, I'm going to start getting numbers that are greater than or equal to 4. So that's positive. But think about it this way. What's negative 3 squared? It's also 9. Is that greater than or equal to 4? Yeah. So guess what? The more negative I get past 2, when I square it, the bigger the number becomes, because when I square it, it's always going to become positive. So that is a weird solution to this. And how will we do this going forward? Okay. Well, again, same thing. We do the square root. But when we do that, we're going to set up 2 boundaries, right? How this would look like is, how I would draw this is x in the middle. X is less than -2. Less than or equal to -2, and greater than or equal to +2, excuse me. +2. My goodness, I was having a moment. So we'd still do the square root, but then we have to evaluate what's going on there and realize there's a gap here where it's not true, but out here it is true. Okay? So let's go on to this last case. Here's another weird case where I want you guys to think about. All right, I have -2x is greater than 10. Now just watch this part. I'll tell you when to write it down, and I'll give you a moment to write it down. For right now, just watch this. So you're thinking, all right, let's just divide by -2, divide by -2. And what do we get? We get that x is greater than 10 divided by -2 is -5, right? So don't write this down, just watch this. So let's test that. That means I should be able to pick points greater than -5, right? Like -4, -3, -2, -1, any of those points. Plug it into the original equation, and I should get a true statement. So let's try it. I'm going to try picking the point -3. So I'm going to have -2 times -3 is greater than 10. Well, -2 times -3 is 6. Is 6 greater than 10? What? Nope, it's not. Okay, let's try this again. Surely if I pick a point way up here, like 4, like +4, right? So I'm going to have -2 times +4 is greater than 10. -8 is greater than 10. What? So there's a thing. Whenever you, so if I divide by a negative, flip the sign, or flip the inequality. So check this out. Let's go ahead, I'm going to erase this, and I'm going to flip it. X is less than -5. Now let's test a point. Let's test the point -6. -2 times -6 is greater than 10. -2 times -6 is 12, is greater than 10. Boom, it's true. And the more negative it gets, the more positive it's going to get, because it's going to be a negative times a negative. So if I divide or multiply, I should put or multiply. If I divide or multiply by a negative, always flip the inequality. So this is actually x is less than 5. So open -5, excuse me. So open dot at -5 and to the left. All right, there's some cool things we're doing right there. We now have this problem right here. I'm going to take a minute and read it to you. You can read it to yourself too. And it says this. It says in 1912, Japan gave the United States several thousand flowering cherry trees as a symbol of friendship. Similarly, the nation of Cameroon plans to give flowering cedar trees to other countries this year. When asked how to decide which cedar tree makes good gifts, Cameroon's chief arborist explains, "We plant cedar trees when they are 6 centimeters tall." That sounds important. So we plant them when they're 6 centimeters tall. And they grow 9 centimeters every year. That sounds important. The trees only flower when they are taller than 150 centimeters. Notice how I just right away start circling information, pointing where it talks about it. Write an inequality to express the growth of the trees. Well, first of all, doesn't this, we planted at 6 centimeters, doesn't that start like a start value, like a B value? It grows 9 centimeters every year. That sounds like a growth factor or a slope. And the trees only flower when they are taller than 150 centimeters. That sounds like an ultimate goal. And taller than, doesn't that sound like greater than? So let's talk about this. So what if I had, all right, I know that I'm starting with 6 centimeters. And every year, it's adding 9 centimeters. So that would be 9x. And then I want this to make sure that whatever this ends up, so however many years later, I want it to be greater than 150 centimeters tall. Do you see how that works? Greater than 150 centimeters tall. And if you guys want it to be in the form of like y equals kind of an mx plus b, there's nothing wrong. You could have written this as 9x plus 6 is greater than 150. That's how I probably would have written it most of the time. But it just, as I read it, this is how I'm reading it. You know what I mean? So it's considered an insult to receive a tree that doesn't bloom. Solve the inequality for x to find out how tall the tree should be to ensure they will bloom within the year. So we want to make sure that this tree is going to bloom the year it's given. Okay? So we want to solve this for what year would it need to be greater than to be able to guarantee it blooms within the year. All right? So we're going to have 6 plus 9x is greater than 150. I'm going to subtract 6, right? 9x is greater than 144. Divide by 9. Divide by 9. What do I get? X is greater than, I think it's 16. Yeah, I solved it earlier. So you can use a calculator, but it's x is greater than 16 years. Remember, x is years. So, how tall the tree should be to ensure it'll bloom within the year? It needs to be more than 16 years old. It's a long time to wait for a bloom, right? Later, the arborist added, I almost forgot to tell you, when the trees become very old, they stop flowering. Make sure you choose trees that are no more than 240 centimeters tall. All right. So, I need it to be greater than a certain boundary, but I also need to make sure it's less than another boundary. So let's solve this. It's still growing at 6 plus 9x, but now I want to find out what happens. I need it to be no more than would mean less than or equal to. No more than means it can get to that, but not past it. So I want this to be less than or equal to 240. Go ahead and take a minute. I'm going to pause it while I solve it. Go ahead and solve it too. I'll let you know before I unpause it. Remember, you're going to write a full sentence. By the way, don't make the mistake of just because you're subtracting doesn't mean I flip the sign. It's only when I multiply or divide by a negative. So I have a lot of students that transpose that, don't do it. Okay, about to unpause it, so if you need to pause it so you can finish, that's fine. But what have I found? I found that it needs to be less than 26 years old. So I want to show you how we would display this information. If we're choosing a tree, the arborist needs to make himself a nice little number line. There's only 2 numbers we care about. Remember, I'm not worried about your skills making a number line. I'm assuming you have them. So my lower bound is 16, and my upper boundary is 26 years. Right, years. What do I know? Well, we said it has to be greater than 16 years. That's an open dot at 16. It needs to be less than or equal to 26 years. So if it's greater than 16 years, it's going to go this way, right? And if it's less than or equal to, closed dot there, I forgot, 26 years, it's going to go up and go this way. And what do? We shade in between. And then we can say the arborist can pick a tree more than 16 years old up to 26 years old. Period. Or however you want to word it. So, this is how we can use an inequality. This is actually a real type of problem. They use this type of stuff in business to figure out when they should sell things, when they should not sell things, at what point they're going to, their cost is going to exceed the amount they're going to make in terms of, because remember, when you're making something, it's not just the cost to make it, it's the cost to ship it, the cost to package, or the cost to package it, the cost to ship it, the cost of employees needed to help sell it, stock it, all that good stuff. So they use this type of math to find that. All right. Peace out.